What do we talk today? I think we have gone through enough of, I think, preliminaries. I spoke a few classes about all of those things. So now we'll get into the core algorithms, right? We'll try and do this. The other thing I wanted to ask is how many of you have installed Qiskit and all now? Has anybody done that? You guys installed Qiskit? Nobody. Yeah. Install this. This is a Python-based quantum computing simulator. Install it. If you are interested, just install it. It's just pip install. Okay. Just in Anaconda, in Conda, create another environment and install it because I want to start coding using this now. So I think we've spoken enough about all the preliminaries, right? Today we'll talk about something called Grover's algorithm. Anybody heard about it before? Nobody? Okay. So this one is good. This guy, for a change, is an Indian. So it's good. His name is Love Grover. Okay. Love Grover. I guess love as Lava Kushan. Right. So he's a computer scientist. Worked all over University of California. So the various California universities, right? UCLA, UCSD, and all of those things. UC Berkeley. So he's a professor, he's a computer scientist. So this algorithm is named after him. Right. So there are 2 or 3 very, very famous quantum algorithms, right? People, I don't know, guys, give me some feedback because if you've been in this class, I'm sure you heard about Shor's algorithm. Anybody? Okay. So usually the Shor's algorithm is the most famous algorithm, right? Anik or somebody or Amar or someone.
Yeah.
So this is the most Akhil, this is the most famous algorithm, right? This is the factorization algorithm.
Yes.
The second most interesting one is the Grover's algorithm, which is a search algorithm, right? So what is this idea? Today, depending on time, we will talk about what this is, how is this the conceptual understanding. I also want to talk about an implementation of this, and I also want to talk about a Qiskit implementation of the same. We'll see how far we get. Okay. Depends, because this is an important algorithm. Next time we'll talk about Shor's algorithm. Once we finish these 2 algorithms, we will try and start getting into actually writing some machine learning algorithms and things like that, right? So we'll actually and in here, whenever there are concepts that we haven't touched upon, I will talk about the concept again. Okay. All right. And if you don't understand, feel free to ask. Okay. If I know the answer, I will tell the answer. If I don't know the answer, maybe we'll all go and find out later. So what is Grover's algorithm and why is this so important? See, basically, let's think about it like this. If I give you a set of numbers, right? Let us say I give you some set of random numbers. 1, 3, 7, 6, 5, 4, 2, 3, 4, 5, 6, 7, whatever. Again, 6 and 8, let's say. Okay. Some 10 numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, maybe another number. So that is 9, 10 numbers, right? From 0 to n minus 1, right? Some 10 numbers. And if I ask you to find a specific number in this, if I ask you, it's some unsorted list of numbers. And if I ask you to find a specific number, let's say find number 6. Correct? How many, maybe number 6 is not a good thing. So yeah, maybe let us make it whatever, 1 again here. So it's just 1 6. Let's just imagine there is one unique 6. And if I ask you to find 6 now in this list, What do you think is the time complexity? Like how many iterations would you have to do to actually get that number 6?
Order of n.
Sorry?
Order of n.
Yeah, order of n. So here, see, best case scenario, if 6 was the first number, you would probably get it in 1 itself, right?
Maximum.
And if 6 is the last number, you'll have to do 10 times you have to search. Correct? So on an average, you have to do n by 2. Correct?
Yes, correct.
So on an average, you have to do n by 2, whatever n number is. So this is kind of how your classical algorithms will work, right? Which is approximately order of n. Everybody knows this sort of notation, right? Order of time complexity of an algorithm. And see, there are a lot of very complex things people have tried. Computer scientists and number theorists have been trying, but we have not really been able to improve this a lot. Okay. The best classical algorithms still work order of n. Now, what does Grover's algorithm claim to do? Grover's algorithm is a quantum algorithm, and it claims that it can do this order of root n. So it's a quadratic speed up, right? Imagine if you have a list of million numbers, then your Grover's algorithm can probably do it in 1,000 steps, whereas your conventional will take a million steps, order of.
Yeah.
So this is a good amount of speed up. We'll see how this will achieve this, but is it making sense why this is important?
Yes, really.
Yeah.
Yes.
So typically the way we do it is n equals 2 power n. It just becomes easier. If I have this as some multiple of 2, some exponent of 2, because then we can represent it in terms of bits exactly. Because we're going to finally use qubits, right, which have 2 states, binary. So your capital N you can assume to be 2 to the power of n. So 10 is probably 2 to the power 4 or something you can assume. It's actually a little more than 2 power 3, but you can say 2 power 4 and get away with it. Okay. So this is what it is. So I think at this level, everybody kind of understands why this is important in the sense. A lot of practical applications, right? You can talk about cryptography. You can even talk about all sorts of search algorithms and things. And see, one more thing you need to understand before we move along and to see why this is so critical. You have P and NP problems, right? So P problems are those that can be solved in polynomial time. And NP problems are such where there is no algorithm that can solve in a polynomial deterministic time. Those are your NP problems, non-polynomial deterministic. Now, there are a set of problems for which you cannot find a solution in polynomial time. But given a solution, you can check whether that is the right answer or not in polynomial time. Right? Those are called NP complete. You guys know this, or do you want me to explain this a bit?
Is the prime factor
Sorry?
whether the prime factors actually we can check that whether.
Yes, prime factorization is a good example. It's an NP complete problem where you cannot factorize a number into its primes, but given its prime factors, you can easily check whether that is a solution or not. Similarly, a traveling salesman problem, right?
Yes, traveling.
It's also an NP complete problem. You cannot find the optimal solution, but given a solution, you can check whether it is
taking less time or not.
Yeah, in polynomial time. So that's also an NP complete. So Grover's algorithm works very, very well for NP complete problems. And we'll see why. Okay. So for problems which are generally NP complete in the search or cryptography and space like that, this is a very, very useful algorithm. Okay. Again, so what happens is I kind of know what I know and I try and tell you guys, but if you ask me, it becomes better for me to kind of get into something a little more interesting, right? So you can define your f of x as.
We need to obviously discuss this with the non-gender as well.
Yeah. So let's define a function. Let's define an oracle such that there is some function which maps from the domain of 0, 1 to the power n. That basically, so first let's understand with where n is 2. Okay, let's say where n is 2. Where n is 2, what are your all of your input strings? 0, 0, 0, 1, 1, 0, 1, 1, right? Those are the 4 possible combinations. And you are defining a function from here to 0, 1. Such that the function f of x is 1 for x equals w, 0 everywhere else. So basically you're defining a function such that that function on, let us say this, let's say 1, 1 is this special entity that I'm interested in. So the way this function works is this function returns 0 on each one of these things. 0, 0, 0, 1, 1, 0, but returns 1 for 1, 1. And this function is a black box, right? In our terms, we call it an oracle, right? When I talked about the Deutsch problem, right? We talked about the Deutsch problem in my first class that I kind of took. If you kind of remember the Deutsch oracle, we defined an oracle, right? It's a black box. It's a function where this function on this particular input string is 1, on everything else is 0. And our problem is to find that 1, 1, or to find that particular string where it gives the value 1. Correct? So that is the solution. This is just same thing as I told last time, but reframing. In our question where I said there are numbers from some random 10 numbers and I said I want you to find 6. You can define a function where function of 6 is 1 and function of every other number is 0. Correct? And you want to find out that input where that function returns the value 1. Clear? Till now it is clear, right, guys?
Yes, clear.
Okay. So you just have to find that input string where the function returns the value 1. In classical computer, how much will this take? This will take 2 to the power n calls, right? You have to check once here, check once here, check once here, check once here. Where n equals 2, it is 4 calls. That's it. That's how your classical computer will work. Yes, you can parallelize it and do all of that, but that is just, yeah, you can say for each thing I will do parallelly and sequentially and all of that, but the process is essentially sequential. You still have to do 4 times. You have to repeat the process. That's the time complexity. Now in quantum, we are saying we can do that in square root of 4. That is in 2. If n equals 2. If n equals n can be any number. Of course, in implementation, we generally implement 2 or 3 because simulations beyond that get difficult until and unless you have a true quantum backing. But that's fine. So at least the framing of the problem is clear.
Yeah.
So now let's see how Grover's algorithm works. So basically, another way to think about it is this. You can think about this as the set of all the values 0, 1, 2, n minus 1. And there is some special value here, x star, and you want to find this. Where f of x star equals 1. F of everything else is same. This is the framing. I'm just repeating this again and again because this is important. There cannot be any confusion here. Now, see, we'll conceptually understand this first before I get into how we will implement it. There are two things that you need to understand if you want to understand Grover's algorithm. One is called phase inversion, and one is called inversion on the mean. And let me talk about both of them in a little bit detail. So let's talk about these two circuits. Okay. One is called a phase inversion circuit. And firstly, let's understand what is phase inversion.
Shrikant, whenever Nagendra is back at work, let's do a quick.
See, here is the thing, right? You all understand at this point that the way quantum computing works is you have a set of alpha x, right? You have something summation on the ket x, right? Over all x's. Each x has a particular alpha associated with it, which is the amplitude, and all of these alpha x's are complex numbers. Right? So this is how it is. This is the superposition state. So how do you get any answer that you want? If you logically think about it, the amplitude of the right answer here should become high and the amplitude of everything else should become low. If you are able to do that, you will get your answer. Correct?
Yes.
As simple as that. It's because you've got the whole thing, superposition, x qubits. They're all inputs, all in some amplitude. Now, the trick is all quantum algorithms, whether this one or any other quantum algorithm tomorrow we write, whether for machine learning or whether for any other process that we write. The thing is very simple. You have to write it in such a way such that the amplitude of the qubit which has the correct answer should become much higher than everything else. If you are able to do that and then you measure it, more often than not, you will get the right answer. Correct? So that is the first simple thing. You have to understand this because everything we do based on this. Now, let us say there is some set of amplitudes. Right? Let's say these are the amplitudes and these are the 0 to n minus 1 qubits, right, that you have. And let's say the amplitude is something like this. Okay. The amplitude of all the qubits. Now we know that there is some special qubit here.
Yes.
Called x star, right? That's what we want. We know that's the right answer. And we don't know that's the right answer. See, the Grover's algorithm assumes that there is one right answer, at least one right answer in the set that you have given. If there is no right answer, then it's not going to return anything, but it's going to waste a lot of time. And here we are taking the hardest case. We are saying there is only one right answer. If there are multiple right answers, of course, the probability of instead of just one x star, if you say there are 3 x stars, then there's a higher probability that you will find at least one of them. No? So the complexity will automatically be lower only than whatever we are saying. We are taking the most difficult case where there's only one right answer. So let us say this is something to the left of it, and this is something to the right of it. What is left of it is nothing but x star minus 1, and this is x star plus 1, let's say. So the first step that we have to do is it's called phase inversion. So we should pick this fx star and sorry. Maybe I should write it a little bit to the side. Negate the amplitude. That is phase inversion. Phase inversion just conceptually means you take the superposition states, okay, which as I said is nothing but sigma of x alpha x at x. It's not alpha alpha, it's alpha x. Okay. From x equals 0 to n minus 1, and that's fine. Just do that. And then you, for whichever the f of x star equals 1, the oracle that you have defined, for that, reverse the amplitude, negate it. If it is plus half, make it minus half. Okay. Whatever the amplitude, just negate it. Simple. So basically, here, if x equals x star, then the amplitude becomes minus alpha x cat x. That's it. In fact, to be precise, you can say. That is what you have to do. You have to negate. So this is called phase inversion. Okay. We will see how to actually do this. But first, so conceptually it's clear, right? It's very simple what I'm trying to do. Step one, I have just inverted the phase, which is I have inverted the amplitude. And please remember, the probability is the square of amplitude. Remember that square of amplitude is the probability for each state. Till now, clear? So what is the next step we have to do? Next step is called inversion about the mean. I will write it down first and then I will explain how this works. If the superposition states again are alpha x, then mu or mean is simply defined as sigma of alpha x divided by n. Right? That is the average amplitude. This can be, so your reversal about the mean can be defined as 2 mu minus alpha x, which can be also written as mu plus mu minus alpha x. Right? I just wrote 2 mu minus alpha x as mu plus mu minus alpha x. So it is basically very simple. So the whole thing, if you kind of, and I will explain how this works, but first let's just see this. So ket equals, you just do an inversion on the mean, that's it. So this is it. So every value you just invert. So what does it look like? If you had amplitudes like this, for example, once you invert, the amplitude should look like this. If you think this is sort of the mean value, it will look something like that, right? So you're just reversing. You're just inverting all values on the mean. That's what you're doing. And you do this using this formula. And how is this helpful? How does this actually work? Phase inversion and inversion about the mean, right? How does this help solve our problem, which is fundamentally to say that we have to increase the amplitude of the right answer and decrease the amplitude of everything else. So how does that work? Clear till now, guys? Do you understand what I'm trying to talk about?
Yeah, Srini.
So now we'll see how this will work. So see, in the initial state, the initial superposition state, let's say you have taken all of those qubits and ran them through a Hadamard gate. So uniform superposition. When you create a uniform superposition, all of the values will have the same probability, right? What will be the probability? Well, sorry, the amplitude, it will be 1 by root n. Why 1 by root n? Probability is the square of amplitude. So the probability will be 1 by n, no, in a uniform distribution. There are n values. So what is the probability of each value? 1 by n. Correct?
Yeah. Yes.
So the amplitude is 1 by root n. Correct? So this is going to be your initial condition, right? Once you do the initial superposition and put it out there, this is how the values will look. Is it making sense, guys, till now? Then you do a phase inversion. So what is a phase inversion? There is some value here called x star. And you are negating the amplitude, right? Correct?
Yes.
Once you do this, what will happen? The overall average will come slightly down, right? Correct. Because in the initial stage, the average is the same. Because everything has the same value. But now one of them you have inverted, so the average will come down. Now again, is this fine? See, the reason I'm asking is I'm not very sure, because I just don't want to keep saying stuff if you're not getting it. I hope you're getting it. Or otherwise, I'll probably pretend that if you don't understand, you let me know, which also is fine, probably. I don't know. So I'll just go on. It's very difficult to teach in sort of virtual situation for me. Right. So when you do an inversion against inversion about the mean, what do? You are kind of trying to invert this about the mean. Correct. So you're going to try and take this and invert it. Going to take this and invert it. Going to take this and invert it. You're going to try and take this and invert it. So naturally, what is going to happen? It is 2 mu minus alpha x. So naturally, what will happen? This, because this is 1 by root n. Now this is what? Minus 1 by root n. Correct. So it will go minus 1 by root n, 1 by root n, and another 1 by root n. So the amplitude of this will become something like 3 by root n. Correct. Once you invert it across the mean. And the rest of it will also invert, but that will invert much lesser. The probabilities of the others will change much lesser. They will probably just come right here. Correct? Making sense what I'm saying here? Conceptually?
Yes, Srini.
Yes.
It is such a common sense. You started with an amplitude of 1 by root n. You did a phase inversion and an inversion about the mean, and the amplitude became 3 by root n. 3 by root n is greater than 1 by root n. It's 3 times greater than 1 by root n. So you have, by doing these two processes, you have managed to increase the amplitude of the right answer. So you're there conceptually with me. So this is what you've been able to do. Now, if you do, and if you repeat this cycle again, like we repeat in Grover's algorithm, we repeat this process of phase inversion and inversion about the mean multiple times. We repeat this process again and again. So when you repeat this process multiple times, you keep increasing it. You keep increasing. It will become whatever, 5 by root n, 7 by root n, And typically we want to get it to 1 by root 2. That's where we want to get the answer. When I say 1 by root 2, the probability is half. So half the time you will get the right answer. You might say, boss, half the time I will get the right answer, so half the time I'll get the wrong answer also. What is the point? It doesn't matter. No, if your probability is a half, you run it 2 times or 3 times, and then you're pretty much certain that you've got the right answer more number of times. Correct? So it doesn't matter. If the probability is half, it is, even if your probability is 1%, it is great. Because even if your probability is 1%, what is there? You run it 100 times. Or you run it 200 times and you will know whatever repeats. Because the number of n's that you're talking about is many, many times more than 100. You typically talk about hundreds of millions. So if there are hundreds of millions of options, if you get something as 1%, it is brilliant. Correct. But typically you will get it up to an amplitude of 1 by root 2, which is the probability of half. So you run it a few times, 3-4 times more at the end, and that's still order of root n only, because 2 or 3 times is not going to change the order. That's a constant order, and you'll get the right answer more number of times. Making sense?
Yes.
So how do we know that it takes root n steps from get to here? That I haven't told you, right? I've just told you that we have to keep, yes, it increases, but how do we know that it actually gets to 1 by root 2 in root n steps? Now that's something, let's actually see how that calculation works. But I hope you're getting the conceptual understanding of Grover's algorithm. We'll talk about implementation, but this is the So now let me ask this question, guys. Now, when the amplitude, let's say when alpha of x star equals 1 by root 2, okay, then what about the amplitudes of the rest of the x's? Right? x1, x0, x1, x2, x3, up to xn minus 1. So what about all of those amplitudes? Each of those amplitudes will be at least 1 by root 2n, right? Because if this is 1 by root 2, everything else there is also 1 by root 2, because if the probability of x star is half, then the probability of everything apart from x star is half. But there are n of those, so it's 1 by, yeah, you can say n minus 1, but it doesn't really matter for our calculation. Yes, in theory it is n minus 1 because 1 you have taken, but that's fine. Just writing it n makes the calculations easier. Anyway, it's not, when I'm doing an order of, it doesn't really matter. Is this clear? Is this logic of why I said it's 1 by root 2n? Okay. Madhu, okay. Anit, okay. Akhil, okay.
Yeah, Srini.
Yes, Srini.
So now let's see why is it root 2n steps, right? Are you finding this algorithm interesting? I found it very interesting when I read it the first time. I don't know how you guys feel. I get excited even today. Okay. This is something. So we are saying each one of these amplitudes is greater than 1 by root 2n. Because that's why that's what I said, right? So what is the improvement per step? This is what it is. So the improvement per step is 2 into this. So 2 by root 2n, correct? Which is nothing but root 2 by n. So this is the improvement you will get per step. And where you have to get to, how many steps? You want to get to 1 by root 2. And per step is root 2 by n. This equals something like root over n by 2. Root over capital N by 2. Which is same as order of root n. So in order of root n steps, you should be able to reach to something like 1 by root 2, which is the Grover's algorithm's proof actually. See, the interesting part about this algorithm is we have not used any complex mathematics at all. It is so simple to understand. It is so conceptually clear. And it's one of those fantastic algorithms in quantum computing. Okay, most other quantum computing algorithms that you actually see are very, very, how do I say? They will actually involve a lot of complex analysis and things like that. But this one, and even Shor's algorithm for that matter, the genius is they have not used anything great at all. It's very, very simple. And they are able to get here, right? So this is order of root n. Is this sort of fine? So I think this sort of should give you a conceptual understanding of Grover's algorithm. Now we will see how it is actually implemented. Is that fine?
Yes.
Okay, good. So now let's see implementation details. How do we actually implement it? And then I don't think there will be time today, but next week we will write code for this in Qiskit. So for next time, I want everybody to have installed Qiskit on their machines. And there is a thing called qiskit.org. Go out there and do some introductory. It's very simple. It's just how to build a quantum circuit, how to run a quantum circuit and things like that. So that I actually want to write the code for this online. Okay. So we will do that next time because I don't think we'll have time today to get into the coding part, even though I wanted to. And then we'll do the same with Shor's algorithm. So that will have two famous algorithms you would have conceptually understood, the implementation and the coding. So then we can start diving into actually trying to understand, build support vector machines and k-means and linear regression. For example, how do you write regression models in quantum computing? So we'll start getting that. But these two algorithms are so key that it's not good if you say you have attended a quantum computing course and you don't know how Grover's algorithm or Shor's algorithm works, right? So now, if you look at phase inversion here, okay, so how do you do phase inversion, right? So you have what? Sigma x, alpha x, ket x, right? So this is your state of your input vectors. What do you need to convert it into phase inversion? You got to pick out the one x, which is the right answer, and invert the amplitude. So another way to think about this is you can say of x alpha x minus 1 to the power fx ket x. Now, what do we know about function of x? It gives the value 0 everywhere except where x equals x star. Correct? Correct or not? So you plug it in there, what happens? It is simple, right? If f of x equals 0, minus 1 to the power 0 is what? Come on. I need an answer. Minus 1 to the power 0 is what? Anik, Akhil, Madhu, Amar.
Anything to the power 0 is 1.
Correct. Thank you. मेरा इज्जत रख लिया. So minus 1 to the power 0 is 1. And what is minus 1 to the power of 1? Minus 1. Correct. So where x equals x star, this inverts the amplitude, right? So this is the function you need to implement. Now, how do you implement a function like this though? Okay. Now, see, there are two ways to understand this. I will probably tell you the easier way, and then if we have time, I will go into the more difficult way of trying to understand this. Did I talk about the Z gate when I was doing an introductory session, or did I not talk about it? Okay. In quantum computing, there is a gate called, all of you know the conditional NOT gate, right? The C NOT gate. People remember C NOT gate truth table?
Yes.
Conditional NOT. If the control bit is 0, nothing happens. If the control bit is 1, it reverses.
Reverse.
Yes, I remember.
Correct. That's the C NOT gate. Now there is a gate called CZ gate. Okay, tell me one thing. People, do you guys know what is the XOR gate? Exclusive OR gate? Tell me the truth table for an exclusive OR. Let us see how much you remember an exclusive OR.
Odd number of ones are there.
Right? What is an XOR gate? What happens when both bits are 0, 0?
Zeros.
If you pass two bits with values in 0 and 0 through an XOR gate, what comes out?
0.
0.
0 and 1, what comes out?
1.
1.
1.
1.
1 and 0, what comes out?
1.
1.
1 and 1, what comes out?
0.
0.
0.
This is the exclusive OR gate. Now, there is a quantum. Is this gate reversible? Firstly, is an XOR gate reversible? No, right?
No.
The XOR gate is not reversible because if you get an answer 0, you don't know what were the inputs. You cannot confirm. It's not a reversible gate. It's a classical gate. Now, let us see a gate called the Z gate. In quantum computing, we use a gate called the Z gate. Maybe I did not talk about this gate beforehand, so maybe I will talk about this. See, the unitary operator, the matrix for a Z gate is this is the unitary operator. This is the matrix. It works like an XOR gate, but within the quantum world. Okay. So the unitary operator. Now, if you have this 1, 0, 0, -1, and let us say you have a qubit which is 0, which is 1, 0, what comes out? Do that. Do the
1
kind-
0
Do the multiplication.
1 0
Tell me.
1 0
1, 0. Correct. What comes out if it is this?
0 -1.
Correct.
Yes.
So what is this doing? If it is 1, it is reversing the amplitude. Correct.
Yes, 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 yes.
If it is 0, it is not reversing the amplitude. And what did we have to do? We had to do this. So a great way to implement this is using a Z gate with a conditional Z gate, which basically means if the control bit is 0, then don't do anything. If the control bit is 1, then do the negative.
Yeah.
So you use this and you can implement phase inversion by doing a conditional Z gate. Okay. You can in your spare time check that this is unitary. In the sense you put it twice, you will get the same thing back.
Hmm.
Okay. The Z gate is a unitary operator. So complex conjugate of this is the same and all of that. So U equals identity. Okay. It's also an Hermitian operator, by the way, if you are interested. Okay. It's also an Hermitian operator, but that's fine. For now, we don't need the Hermitian property of this gate for this particular circuit. So the phase inversion can just be solved by using a conditional Z gate. It is called a CZ gate. Okay, in quantum circuits. But if you put a CZ gate, you will get this, which is what we want. You can even derive it from first principles, but I will probably do it some other time just because we will not have time to get into the inversion. But you can even derive this from first principles. You will get the same answer anyway. So it's a conditional Z gate. It's very simple. Phase inversion is simple. You implement it using a conditional Z gate. And if you talk Qiskit or if you talk IBM quantum computer or anybody, all of them give this gate standard. So you can just put the gate. That's it. You don't have to do anything. It's like you can just define the gate on your superposition. So see, any quantum computing is very simple. You take set of bits, you first run them through a Hadamard gate. What do you write out through a Hadamard gate? To get the superposition. Once you get the superposition, you do whatever gates you want, conditional Z gate, this gate, that gate, you do whatever gates. And at the end of all of it, you again run it through a Hadamard gate to get to the measurement. Actually, you measure them, right, to get whatever value you want. Now, the next one is probably it's not complex, but maybe a little bit more linear algebra, which is inversion about the mean. Okay, and then we'll put all of it together, and then you have an implementation of inversion about mean. How do we implement inversion about the mean? So again, this is nothing but everywhere understanding that capital N equals 2n. So now I'll first draw the circuit and then kind of explain. This is kind of, it's not too tricky or something, but let's just understand this. Okay. So you again pass it through a Hadamard gate. This is some Hadamard gate tensor product with N, right? And then this is some special gate that we will use. Okay. Let us call it some U not equal to 0, because essentially that's what you want to do. And then you've got another Hadamard gate that I said. You need another Adamat gate, one more time tensor product, and let's say you got all these inputs and you got all these inputs going in and you got all these inputs coming in. Of course, you have some control bit out here, some control bit out here, which is just the control bit, so you don't have to worry about. So what is the point here? The point is you can very simply think about another function. Okay, think about a function g, which is 0, 1, n, again map into 0, 1. Now here is the thing. Where all of them, the g of all of these inputs, if everything is 0, the g should return 0. So the g of f of if everything is 0, for all the things where f of x returns 0, this should return 0. And g of some this y equals 1, where everything is not 0. Right? Where y is not equal to all zeros. You understand what I'm saying, right? Because see, if you have all of those things, somewhere the f of x, some f of x of one of this has to be 1. That's the assumption. And that's the one that you got to find out. That's the one that you want. So you can think about it like, you can call that as y, that f of x as y, and then you say g of f of x equals 0. If the whole thing is 0, it is 1 if all of them are not equal to 0, if at least one of them is equal to 1. This makes sense till now, what I've said?
Yeah.
In fact, let me draw it geometrically a little bit. Maybe you will have a little better intuition. Yeah. Now, inversion about the mean can geometrically be understood like this. Let us say you have some vector psi, which is nothing but our state space, our vector in the state space, which is sigma of x, alpha x at x. And let us say this is some vector u, where u is nothing but the mean. Okay. Now, the inversion about the mean can be geometrically understood as a reflection on this vector. It can be understood that if you reflect this on the mean, what you get is the inversion about the mean. Makes sense, right? It's just a reflection. On the mean, you're just reflecting it. Then how do you do that? How do you do this reflection? You take another vector, usually, which is orthogonal to u. You call it some vector w. If, for example, here you take all the x's to be zeros, then anything which has got 1 will be orthogonal, right, in that basis. So nearly orthogonal. So this is a vector that is orthogonal to that vector. Then you just need to this part of psi you kind of map onto the orthogonal thing, take the negative amplitude, then you will get this vector. And then here you simply do the reflection. So for whatever is on this, now you get the u component of this w dash, which will be this. Thus, this vector will be the reflection of psi on u. Is this making sense? See, this vector, see, ideally what you have, if you have g of y's, you have all of them as zeros with some same amplitude. And one of them, just one of them where zero, this will give the value of 1. Because one of them. And our thing is to figure this one out. So what I'm saying is, you take this as the u vector, reflect your psi vector on this, it will increase the amplitude of this. That is all that we are saying. And of course, once you transform, you convert it back. Use another Hadamard here and convert it back to u or to wherever, because you convert all of this to zeros. The reason you convert it to zeros is it's easy to do the operation. Doesn't need to be, but you do it all zeros, then you reflect it, and then you convert it back. That's it. That's the simple reflection operator. Okay. I'm hoping it's making some sense. Maybe I've confused you more by giving you a geometry perspective. Not, I'm hoping it's not confused you either. So what is the thing? So basically, the way we wrote it is, there is some tensor product. And this needs to be some unitary operator is what we said to do the inversion. So now what happens if you do the Hadamard operation, all of them are 1 by root n, 1 by root n, and then you do one. I don't know, maybe I'm getting a little more abstract for you guys. Should I do this way or not? I'm thinking, are you guys having trouble following me here, or should I? Tell me, should I go about this, or are you feeling that you're kind of lost? Or maybe should I spend more time? Maybe next class I should again spend more time on Grover's algorithm. Now we have to find this matrix, right? We have to find this matrix that will kind of do this. I don't know. Okay, we will do it in the next class. I see, read complex analysis a little bit more and come to the class. In the sense, when I say complex analysis, read a little bit more about the geometric interpretation of complex numbers. What does reflection mean on an axis? I think read that a little bit and come back, because otherwise I think there will be a lot of confusion here.
Sure.
Okay.
Am I making sense, or should I, or not?
Yeah.
Okay, so I think read a little bit more what you mean by reflection of complex numbers. Okay. If you have a complex vector and you're trying to reflect it in a complex plane, what does it mean? Get the geometric interpretation of that. And then probably it will make more sense, because see, without the geometric interpretation, what will happen is this will just become a linear algebra exercise, which you can write the matrix and multiply, but you won't understand much about what is the matrix and why am I multiplying it in a particular way. So get the geometric interpretation and brush your things. That's just, see, quantum computing is nothing but basic linear algebra and complex numbers. That's all that is. So on those two things, you should not have doubts. Otherwise it gets tricky.